Embedded software development. This is the outline of this video, and let's look at a typical system, a typical embedded system. We saw on previous videos different architectures. This is a simple system that you're going to find inside of ARM processors, and you have in blue your digital peripherals. Here some analog mixed signal peripherals. Notice on how they connect through, notice how they connect through this peripheral bus to a bus bridge before they connect to the processor. And we have two types of bus. We have this APB bus and AHB light bus. So the difference is that this one runs much faster clock than the peripheral bus. This one is used to communicate with flash memory, SRAM, or the boot ROM or high-speed peripherals. But the normal peripherals, if you want to call like that, they use this APB bus peripheral. All the peripherals here connect through interrupts also to the processor. If you have a DMA, a direct memory access, normally this helps with the processor, alleviating the processor. The EMA normally also connects through this high-speed bus and somehow connects through the registers so we can communicate and get information from the registers. Basic concepts, let's go over reset, clocks, voltage level, and inputs and outputs for embedded systems. Embedded systems have a reset button. Typically is done with adding a pull-up resistor so this pin is not floating when I'm not pushing my button. Pull up because its reset is active low. So notice here when I have a 1 negates that, becomes a 0, so the reset is not being done. And then the minute that I press the button, which is active low, that 0 becomes a 1 and resets the microcontroller. The capacitor is a low pass filter. Here is to eliminate the jitter that you have when you push the button. It's a physical button, so it's not going to close instantaneously. So you have a low pass filter over there. For clocks, you can have internal and external clocks. We will dig in a little bit more on your clocks for your platform in a different video, but this is a typical one here, an external clock with a couple of capacitors connected to your external clock pins of your microprocessor. You can also have internal oscillators, but those ones normally are inaccurate and they cannot go higher speeds, higher clocks. Then you have PLLs. A PLL is a good way of boosting. So you connect your crystal, is 12, 20, 30 megahertz, but you want to speed up the clock of your CPU to 100 megahertz, 400 megahertz. So you need to achieve that with a PLL. And a PLL is actually a pretty interesting device. I will have a video also that goes a little bit more into detail of the PLL, but basically you have here your reference signal and the VCO is going to follow or match this reference signal, and then you have the multiplier that is going to give you higher frequencies for your clock. Voltage levels, pretty much saying that you have supply pins for your microcontroller, can go from 3 volts, 5 volts, or even 1.5 volts depending on what type of microprocessor you're using. And then inputs and outputs. Normally you don't have displays or keyboards or mouse, and you need to use peripherals to communicate with your microprocessor, and they can range from I2C, SPI, UART, USB, Ethernet, and then CAN, SD cards, and also if you don't have screens, LCDs is a good way to see information coming out of your embedded system. Embedded program flows, different ways of programming your microprocessors. There are different ways of doing that. Pooling is one technique, interrupt driven, combination of pooling and interrupt driven, and handling concurrent processes. So let's go over each one of them individually. This is a flow chart of a pooling method for a simple application, and it doesn't rely on any interrupt routines. So you have your start, initialize your code, and normally what you do is you have a set of conditions here that are checking for the peripherals, and if it's true, they resume here, call a function, do whatever needs to be done related with that peripheral, and then goes back and continues the code. There are some bottlenecks, some problems, as you probably can already understand. If I'm spending time with this process, I cannot probably attend anything related with peripheral C, so that's one of the constraints with the pooling. So that's why they say will not get any service for some time. That's the main disadvantage with pooling methods. Then we have interrupt driven. In this case, you have your main code, you start, initialize whatever you need to initialize, and then you kind of enter in the sleep mode, you initialize your interrupt routines, and whatever happens with a process or an interrupt happens, you attend the code inside of that interrupt routine, and then you resume sleep mode and you wait for another interrupt routine to get triggered. This is not the best way of programming things. Interrupt routines, you want to be fast in an interrupt routine. If I'm here doing stuff, I'm not able to attend other interrupt routines. So if it's small code, this is probably like you probably get away and it's fine. But if you're doing a lot of code inside of these processes, that's not a good idea. So balance between a pooling and interrupt routine is probably like what you will use the most in a lot of applications. And what you do is you'll have these if conditions peripherals here, checking them, and these are triggered based on interrupt routines. And if that happens, you enter, you do your code, and it's a good way of combining pooling with interrupt routines. A last one, concurrent processes. In some cases, you have so much stuff, so many tasks, so many things to accomplish at a certain amount of time that it's very hard to have just a big loop cycling through all those states. So what you do is you kind of have this concept of states or threads or tasks, and that's how you do it. Like one solution is sequence of states, another solution is to have a real-time operating system that handles those tasks for you. So the first one, sequence of states, is what you guys are familiar with, a state machine. So you do your code, you do your process A1, go to state 2, come out, go back again, do your state 2, go back, do your state 3. So you kind of have this notion of states, and you are responsible to go around these states at a certain speed. And if it's too complex to manage that, then you allow a real-time operating system to do that job for you. So he is going to assign some slots for each task. So you have what it's called an operating system task scheduler. You have your processes, and this identity here is responsible to switch between which process. This is pretty much the way that your computer normally works. What's inside a program? Let's look at an image. So when you press compile, it generates an executable file. And what's inside of that file? Well, it starts with a vector table, contains the starting address of each exception and interrupt. And then you have the reset handler or startup code. This is where you contain some hardware initialization or some startup code that it's directly executed before your main code. Then you have the C startup code, so it's pointing for your main code, also for global variables and any values that you have in SRAM. Then you have your application code, then some runtime library functions, and at the end, other data such as initial values for your global or statical variables. So what happens when a microcontroller starts? That is an order of execution. This is kind of a visual way of what you just saw before. So you have all that information inside of memory, but what is actually happening all starts with reset. You have a bootloader. This bootloader can be an on-chip flash memory, or it can be a separate boot ROM that contains a small bootloader that loads the information from your program into memory. Then you enter in the system initialization. Then you start your C code, your main, initialize variables, and then you do everything that it's inside of that main. Hardware initialization, processing, all that good stuff. Operation modes and states. There are mainly two operation modes, the thread mode and the handler mode. Thread mode is the normal mode when you're executing code normally, and the handler mode is when you're handling any type of exception or interruption in your microprocessor. For a particular family of ARMs, they have also this thread mode for unprivileged access level. So you also have this particular mode over here. And then at last you have the debug state. If you have your debugger connected to your microprocessor, you can go to a debug state that things are running at step by step with your development environment. At last, the software development flow. You are familiar with this. This is a visualization of a previous video that I had that I talk about compiling and linking and assembling your code. So it's just giving you a visualization that your C compiler starts by compiling the C into objects. The assembler looks at assembly source code, generate also those object files. The linker picks up all those object files, all those runtime library functions pre-compiled, links everything and generates an executable file that then is deployed into your Flash through a Flash program or a debugger. This is more an overview, so everything that is done from compilation, assembly, and linker is done on the computer, and then the programmer is done by this in-circuit debugger. There are different ways of debugging the interface. You can either do that directly to the pins of your microprocessor with a JTAG adapter or an in-circuit debugger, or you can have this guy over here, or you can have your tester. But pretty much your development environment connects to this debugger, and then the debugger connects to a specific pin of your microprocessor so you can program and debug your microprocessor.